Hi, everybody, and thanks for joining this session. In this talk, I will let you know about the resources that we have provided in the context of the COVID on the Web project. And as you can see, we are 13 authors on this paper, so this is quite a collaborative initiative. At the origin of this work is the publication by the Allen Institute of the Core-19 dataset. Core-19 stands for COVID-19 Open Research Datasets, and it's been published in early March for the first time at the time of the lockdown. So this dataset compiles scientific articles linked to the family of coronaviruses, not only SARS-CoV-2, but also SARS-CoV-1 and other ones that have been studied during the last 20 years or so. Like I said, it was published in March, initially with 43,000 full-text articles. Now the latest releases are beyond 100,000 full-text articles. So this is basically a very rich corpus, obviously, but also huge, so that it is impossible for a human to read all of this literature and make sense of it. And in the WMIX research team, we are not biologists or biomedical doctors, but we have some ideas about how to extract and process knowledge. So our approach was to say, okay, how can we leverage the tools that we know that we're used to working with to make it easy for the biomedical community to access and make sense of this literature. So pretty soon enough, of course, we thought about the named entities, which is almost very natural when you start dealing with a natural language. And then we started to work with argumentative graphs, and Anna will describe it in a bit more details what this is. And also, not only we were willing to process the data and derive more, say, smarter data, but we were also concerned with how to visualize and to explore the data. So here is I will describe the pipeline that we have set up to analyze the articles. So initially we started with two sets of tools. The first one is ACTA. I will describe it in a moment, which is meant to the extraction of argumentative graphs. And at the same time, we try to run named entities extractors that you would probably know. These are DBpedia Spotlight, Entity Fishing, and Annotator, Bioportal Annotator. So the good thing with these annotators is that they extract named entities and link them with URIs from the web of data, which is cool. So soon enough, we translated all of those data into RDF using an implementation of the XR2ML mapping language, and that helped us produce this COVID on the web dataset. So this was, say, a first step meant to process raw data and derive smarter data. So now you are probably very familiar with named entities extraction, maybe not so much with the extraction of arguments. So let me tell you just a bit more about that. Argument mapping is the process of automatically building graphs of arguments from natural language. So you would typically analyze the text to get from it what we call argumentative components. And then you would classify them into two classes, that is evidence and claims. And the second step, which is here, would be now how do those argumentative components relate to one another with two relations that can be support or attack. So an example would be, for instance, a paper that says hydroxychloroquine lowered the symptoms in X% of the patients. And you could find that this is backed by, supported by an evidence that would say there was some significant change in the measure of some given biological marker and so on. So ACTA is a platform developed by my colleagues Tobias Meyer, Elena Cabrillo, and Serena Villata. It stands for Argumentative Clinical Trial Analysis. And this platform is meant to help clinicians make decisions based on this graph of arguments that are extracted automatically from the articles. It is also capable of detecting and highlighting PICO elements. So PICO elements, this is a framework to answer healthcare questions in evidence-based clinical practice. So you could see Pico elements like as say some sort of named entities that are very much focused on the domain of clinical trials. And ACTA comes with this web interface where you could see here on the right the text that has been analyzed, highlighted of the argumentative components. And here in the middle, you will see the graph of components related to each other. So you have the claims, the evidences, and how they relate to one another with the support or attack relationship. Okay, so now that we have this pipeline to produce an enriched data set, the next step was to figure out how to interact with the data, how to explore and visualize the data. So I just showed that the ACTA platform comes with a web application that allows the visualization of graphs of arguments. And in the case of the named entities, we use different other tools like the Cori's Semantic Web Factory, together with some visualization tools. So some are pretty basic, like Jupyter Notebooks that we experimented, and also the MGExplorer data visualization library. So this is a JavaScript library that explores different visualization techniques, and we kind of repurposed it for the exploration and exploitation of this specific data set. I will show examples. And also we were very much concerned with the publication of an open data set that is complying with the common guidelines and good practices of FAIR data and so on. Okay, so this second step is say how to exploit and explore the data that we have produced in the first step. Now, the last pillar of the project is that obviously we didn't do all of this just for fun. So this whole approach was guided by a user-oriented approach in which we analyzed the needs of the biomedical users, and that was done through different interviews with researchers from the French National Healthcare Research Institute, the National Institute for Cancer, and this whole analysis of needs guided the whole project. So, okay, now what are the kind of things that we can do with that? This question is typically the kind of question that came up during those interviews with biomedical users. So it is, what are the articles from the corpus that mention at the same time a cancer and a virus of the coronavirus family? So to answer this kind of question, in this example, we used the Wikidata URIs associated with the named entities. So we fetched the whole hierarchy of Wikidata entities, classes, and instances corresponding to cancers and coronavirus. We fetched that from Wikidata, and that gave it the opportunity to reason on the whole data set using the named entities. So here you have the beginning of a list of articles that mention one cancer. You have the type of cancer that he's mentioned here and the type of coronavirus. So now, beyond having text results, we also explored how to provide visualizations of this. And this is a representation of answers to the same question, but with an R Jupyter notebook. So it's a heat map, basically. And how you would read this is to say, okay, there are more papers that mention coronavirus together with the leukemia and the melanoma. Another type of visualization was about the MGExplorer that I already cited. So MGExplorer is a JavaScript library that provides different visualization techniques. And here, the idea is to explore the relationships between those entities, the coronaviruses and cancers. So if they are connected here, that means there is at least one article that cites, that co-mentions them. And this library will give you other ways of doing some sort of exploratory search and to explore through the whole data set. So you will be able to visualize clusters of articles that have the same co-mentions, and then explore among those clusters what are the other types of cancer or viruses that are co-mentioned, frequently co-mentioned, these articles, and so on. So just a few statistics about the whole data set. Here in this part, you have statistics about the named entities, and here about the arguments, and the total is here. So overall, the data set amounts to 674 million triples. This is quite a lot. This is not Wikidata, but still, this is quite a lot. Maybe to mention here is that in the case of the named entities, we used, like I said, Spotlight, entity fishing, and annotator. With entity fishing, we were able to process not only the titles and abstracts, but also the bodies. And overall, it amounts to 30 million named entities disambiguated with Wikidata URIs, and that amounts to 564,000 unique URIs from Wikidata. We did not process the bodies with Spotlight and annotator because the data that is produced is pretty huge. The number of named entities explodes, and that doesn't mean we don't want to do it, but for now we had limited resources, so we had to to stick to what we could do, and even then that was quite a large amount of data to process. Okay, so now in terms of fairness and reproducibility, so we have tried to follow as much as possible common guidelines and best practices about publishing linked open data, and as well as fair data. So we have added different sorts of metadata about the dataset using DCAT, VOID, some provenance information with Provo. The dataset has been uploaded to Zenodo, which is good because it gives it a DOI. We have a public Sparkle endpoint. All the URIs are dereferenceable, and we have registered the dataset in the LOD cloud. So if you look at the last diagram that was published in July, this little red bubble here is our dataset. Now, in terms of reproducibility, we have made a real effort to provide an exhaustive documentation about the dataset, about the RDF modeling that we chose, plus all the scripts, the tools, models, configuration files, everything is in the GitHub. It's documented. So our point is really not only to provide a one-shot dataset, but to make it reproducible. Now, I do not say this is a click button thing. For now, it still needs a bit of work, but everything is here. So this is part of our goals to work on this and to be able to automate this much further. Now, in terms of future works, we wish to continue the work that we have started with the biomedical community so as to ensure that our approach remains guided by the needs of that community and aligned with their needs, so that we continue to come up with a solution that really is effective for those people. Second thing, really important, named entities extraction is something that can be very noisy. When you extract named entities, you can have many false positives or many things you're not at all interested in. We are running an ongoing work on the automated discovery of frequent patterns and association rules. And we have a good hope that this would help us train models to detect inconsistent named entities and possibly suggest missed ones, which would be something really good, because you don't have existing data sets already annotated with named entities that would have been done with people. So there is no ground truth here to train your models. Last thing, but not least, COVID-19 is released weekly, actually even now twice a week. This is quite huge, and we need to work on how to automate the production of the data set, so automate the whole pipeline. And in particular, we'd like to be able to update our data set rather than having to recompute the whole thing from COVID-19. And this is all geared towards the whole idea of reproducibility and reproducible science and everything. Okay. So Thank you for your attention. On this slide, you can find the different links to GitHub, to our Sparkle endpoint, Virtuoso faceted browser, and to the Zenodo page where you can download the dataset. And I would be happy to answer a few questions. Thank you very much.